Okay, so I'm going to talk about, well, there's my title, latest on linear sketches for large graphs, lots of problems, little space, and loads of hand waving. I'm rather proud of that title, but it's the sort of title you give to Grigory when he wants an abstract all of a sudden and you're not quite sure what you're going to talk about. So I've decided what I'm going to talk about. I'm going to cherry pick some nice simple results. It's like the end of the second day, you're all tired. So I'm going to present some edited highlights and simplified versions of results from 3 papers here with my students and some other collaborators. Okay, so a lot of what I'm doing, all the work I'm going to talk about and all the work in these papers is motivated by the problem of trying to process dynamic graph streams. So the idea is you want to analyze a massive graph that's given to you, that's defined by a sequence of edge insertions and edge deletions. And you're trying to process these graphs under the normal constraints of the data stream model, so you've got a small amount of space and you want to process each update very quickly. Okay? So the main technique when you're trying to process streams with things being added and deleted, incremented or decremented, is to use linear sketches. And so linear sketches are just random linear projections. So in the case of graphs, you're maintaining random linear projections of vectors and matrices that represent data about the graph. Now, initially, linear sketches have a long history. They've been very, very useful for estimating various sorts of numerical properties, Johnson-Lindstrauss, etc., etc., etc. Initially, there was some skepticism that random linear projections would be helpful when it came to solving combinatorial problems because something like graph connectivity is very sensitive to a particular one edge existing or not. So how useful is a random projection going to be? Well, it turns out that linear sketches have indeed been very useful for solving graph problems, and there's now lots and lots of results, some of which I'll touch on today, things like edge and vertex connectivity, the nice result in spectral classification last year at Stark, matchings, vertex cover, hitting set, correlation clustering. You heard a little bit about from Sodipto, who's somewhere. Is Sodipto still here?
He's back.
Oh, he's back, is he? Okay, awesome. We need your help. No. So rather than kind of go into who's done what, a little plug for a survey I wrote last year that you can read about a lot of prior work. Now, unfortunately, very annoying for me is the community has done a lot more work than last year, so I'll need to update the survey at some point. Okay, so the one primitive the one kind of piece of technical background I need to mention is going to be important in this talk was something that Sanjeev mentioned yesterday, and that's L0 sampling. So the result is that there's a distribution over matrices, M, such that if you give me any vector, x, I can find a non-zero entry from x just by looking at the projection m times x. Okay? And it's actually a random non-zero entry. And the corollary of this is, in the context of graph streams, what it means is I can see my sequence of edge insertions and deletions, and I can pick a random edge uniformly I can pick an edge uniformly at random from the graph using polylog n bits of space. It's not complicated, but it's more time than I have. You can think it's not of the form where it's not one of these matrices where every entry is Gaussian or Cauchy. It's like a very structured. Like the top row is like very dense of ones, and then the next row is less dense, and etc. etc. I can, yeah. Okay, you're welcome. Okay, so but already I can actually kind of mention a new result, given that you now just know L0 sampling, or you already know L0 sampling. And that's for the problem that Kamesh was talking about earlier, estimating the densest sub graph. So you have a graph. The density of a given set of nodes S is basically, if you look at the induced subgraph on S, it's the ratio of the number of edges in that graph to the size of S. Okay, the standard definition. And it won't surprise you to know that the problem of estimating the maximum density, or the problem of estimating d star, which is and the problem of finding the maximum density in the graph is just estimating the max of ds over all possible subsets S. Okay? So there's been quite a lot of work on this problem in the data streams community. 2 particular papers both achieved a 2 plus epsilon approximation using roughly 1/epsilon² n space. That first result took one pass. The second result took, I think, kind of logarithmic number of passes. But they got a 2 approximation, based on some ideas developed by Moses Charaka. So our result is a simple single pass 1 plus epsilon approximation using that amount of space. So I like to think of this as, this is really the simplest possible algorithm you could possibly think of for computing the densest subgraph. I like to refer to this as the densest subgraph algorithm. Like, the algorithm is really simple. You take your graph and you sample n edges from the graph. Okay? And so you now have a subgraph. Okay? Look at that subgraph. Find the densest subgraph amongst your sampled edges and return that. And it works. I'm not quite sure why this was missed in the past. So in slightly more detail, so you're going to sample roughly n edges using your L0 sampling primitive. And then amongst the sampled edges, let d hat s be an estimate for the density of that subgraph based on the sampled edges. And so you just return the maximum density in your sampled edges. Analysis basically follows, I guess, Jelani is also gone, has he? Okay, so basically it kind of follows his patented, is it Chernunian? Yeah, Chernunian. Chernian. So that's better. His Chernian bound. But you need to be slightly careful, just because normally when you apply union bounds, you apply union bounds over a polynomial number of things. When you're talking about applying union bound over subgraphs, well, unfortunately there's an exponential number of subgraphs you need to analyze. But everything works out nicely. Basically, the idea is, with very high probability, if you look at any subset of nodes S of size k, then if the density of that subgraph in the original graph is around about the optimum density, the maximum density, then your estimate is within a factor 1 plus epsilon of what it should be. Whereas if your original density of that subgraph is low, much less than the maximum density, then your estimate is still significantly less than the optimum. Okay? So when I say this happens with high probability, that high densities stay, your estimate's good, and low densities you don't start to look like high density things. So when I say that probability is high probability, it's actually important it's exponentially small in k. Because then, when you apply the union bound, you've got to worry about order n to the k subsets of size k. But because your error probability was exponentially small in k, everything works out and you're happy. So it was somewhat of an open question why this has been missed by people in the past, except this was somewhat answered by the fact that after our paper was accepted, we were emailed by 2 other groups who were independently kind of working along ideas of the same lines. So Mitsumaki et al. And KDD, and Esfandiada et al. Okay.
Question though, what's the role of the scaling by M over T?
Well, okay, so good question. So I've sampled T edges, and now when I look at density in the subsampled graph, like kind of all the densities have been scaled down by roughly T by M. So I should go back and multiply back up by m divided by t.
You want to return the density rather than the...
Okay, if I just cared about finding a set of nodes that had high density or similar density to the maximum density, I don't need to do that scaling. Okay.
How do you solve this subproblem?
Oh, well, then you can do that in post-processing in polynomial time. So yeah, so I haven't addressed... So most of the work in the paper is actually about how to sample these edges quickly as you go through the stream. But ultimately, when you get to the end of the stream, you have a set of edges, and you just run whatever offline algorithm you want on those sampled edges. Okay. Sorry?
But exactly.
Yeah, or you could lose a factor 1 plus epsilon and I think solve it. There's things you can do. Okay, so the general theme of the talk So that was a very simple type of uniform sampling, and I showed you how it solved result number 1, densest subgraph. So the general theme of the talk is, what other types of graph sampling are there that are A, useful in the context of solving graph problems, and B, can be supported on dynamic graph streams? Okay? And I'm going to present 2. One I've decided to refer to as Snape sampling, and this is going to be particularly useful when solving problems like graph matching and more generally kind of vertex cover, hitting set, etc. And the second one, which we decided to call, or I decided to call, deals sampling. Amit almost got Draco sampling to work out as a good acronym, but it didn't quite work, so I went with deals sampling, which is good for graph connectivity problems. Okay, so in terms of graph matching, which I'll focus on, the idea is that, so this is like kind of a parameterized complexity style result. So I promise you that we're processing a dynamic graph stream, and I promise you that the maximum matching has cardinality at most k. So this result says that we can find the optimal matching, so no approximation involved, we can find the optimal matching using O tilde k squared space. The algorithm is optimal in terms of its space use, its polylog update time. The algorithm is very simple. You can extend this to kind of hypergraph matching and hitting set, but it gets very complicated and it's not a result for discussing today. And the basic idea is this Snape sampling primitive. And then the second result is, well, if the matching result is now bigger than k, then you can find a matching of size k by t, so basically a t approximation, in the dynamic data stream model using roughly k squared divided by t cubed space. And so an application of this is if you just kind of guess k in powers of 2, since you don't know k ahead of time, you can get an order t approximation for maximum matching using n squared over t cubed space. This is very similar to the result that Sanjeev talked about yesterday, and those guys proved that that was optimal. It's normally hard to get an approximation factor which is smaller than 1. Yeah, you may have covered this in grad school. Okay. Okay, so Snape sampling. So I know it's late. I know you're getting sleepy, but this is really simple. Okay. Snape sampling. The Snape stands for sample nodes and pick edges. So guess what the sampling procedure is going to be? First of all, you sample the nodes. Okay. You sample each node with probability, say 1 over k. So say those red nodes are the ones you've sampled, and you delete the rest. Okay. And now of the edges left in the graph, you pick one uniformly at random. Okay. And you return that edge. Now, potentially you could have, maybe there's no edges remaining, in which case you just return null. Okay? But this procedure is going to pick a random edge. And if you think about it for a while, it's not the same as just uniformly picking an edge of the initial graph. Okay, okay, so very simple sampling procedure. Any questions? As I said, the clue's in the name. Like, you should be able to remember this entire talk by the stupid names I've given stuff. Snape, sample nodes and pick edges. Sample each edge independently with some probability. Look at the induced subgraph, sample the remaining edge. Okay, what I think is kind of a nice, cute result, and not too hard to prove, is that if you just repeat this process k squared times, you'll generate a bunch of edges, and the result is that if the original graph had a matching of size at most k, then amongst the sampled edges, you also have a matching of size k. Okay? So you can think about this in terms of, if you're familiar with kind of kernelization and parameterized complexity. So this is essentially kind of kernelization via sampling. Okay, any questions so far about the statements? Because I'm not going to go through the entire proof in detail. I'm going to give you enough so that you can work it out on the train or the plane back home. Or if you're really awake, you can work it out now. So the basic idea is as follows. So let's say G, our original graph, is a graph where the maximum matching is of size at most k. Okay? And we're going to say that a node is heavy if its degree is more than 10k, and an edge is shallow if both of its endpoints are not heavy. Okay? So as an example, here's a graph with a shallow edge there. Here's a graph with a heavy node here. We'll assume that In this case, 1, 2, 3, 4, 5, 6, 7 is a high degree. Okay. So here's a lemma that's fairly intuitive. Let's suppose you've got your graph G, which has a maximum matching of size at most k. And let's suppose you've got a subgraph, G prime, such that all shallow edges in the original graph are in G prime, and that for every heavy node in the original graph, you've got at least 5k incident edges on that node in G prime. Okay. What this means is that the only edges that G prime is missing are edges incident on a heavy node. We've already but you've made sure you've remembered enough other edges on the heavy node. So the idea for proving that G prime contains a maximum matching of G if these things are satisfied, it just follows because you can argue that for every missing node, for every missing edge, for every edge that's missing in G prime that was originally in G, it must be incident to some heavy node, like this guy. But you've remembered so many other edges incident to that node that the fact you've lost 1 or 2 is really not going to affect the best matching you could get, because even if this was something in your matching, you can instead use one of these edges, because all the other endpoints kind of been used in the optimum matching. Okay. So a useful fact that we're going to use going forward is that because G has a maximum matching of size at most k, it's got a vertex cover of size at most 2k. So any questions so far? Okay, so all we need to prove is that when we do that sampling procedure, when we pick order k-squared Snape samples, that we get all the shallow edges in the graph, and for every heavy node in the graph, we get at least, say, 5k incident edges. And actually, once I've broken it down to that, that's the sort of level seriously you could go and work that out. Let me just flash it from slides just to give you some hints. So for the shallow edges, the idea is, remember the first stage of the sampling process was picking some edges and deleting some other edges. If you delete if this is your original graph, and this is a shallow edge, if you delete all edges in the vertex cover, except for maybe U and V, then all remaining edges are incident to U and V. And then if you delete all neighbors of U and V, apart from each other, then the only edge you're potentially left with in your induced subgraph is the edge between U and V. And if U and V are both sampled, this is the single edge remaining in your induced subgraph when you do the Snape sampling, so therefore it's one you're guaranteed to return. So the probability that you didn't pick nodes in the vertex cover and you didn't pick the neighbors, you can work out to be something like 1 over k squared. And so you're repeating this process order k squared times. So after order k squared log k repetitions, we've sampled that shallow edge with high probability. Okay. It's kind of a cool effect, but not deliberate. Okay, so edges and heavy nodes, similar sort of idea. For every heavy node U, if you delete the edges, if you don't pick the edges in the vertex cover, and there's not that many of them, remember, there's only 2k of them, then you're going to be left with a star on U that has many leaves. So like say this star. You could have lost some leaves because they might be in the vertex cover, but you wouldn't have lost that many. Okay? And again, it's possible to show that with probability 1 over k now, in the induced subgraph that arises in the Snape sampling, you have at least one edge amongst that star with probability 1 over k. So if you repeat k squared log k times, you're going to find order k, maybe 5k if you make the constants work out, 5k edges incident to U. And that's pretty much it. I didn't go through these calculations in detail, but there's nothing weird going on, nothing complicated. So that was the result for small matchings when I promised you the matching was at size most k, and the analysis basically went through analyzing probability the vertex cover disappeared and some other stuff. The analysis for the approximate case is slightly different, but equally simple. So if G has a matching size more than K, then I claim that K over T cubed Snape samples, where the probability of picking nodes is now T over K, has a matching size K over T. So it's that T approximation business again. And the idea is, well, imagine this is your sequence of Snape samples that you got from that very simple sampling procedure. Now, in some of those samples, you may have ended up with an empty subgraph, an empty induced subgraph. So some of these things are kind of nulls, or kind of some of the sampling steps failed, but in the other cases, they're actually edges. And so one way to do the analysis is to consider building up a greedy matching as you sample those edges. So you sample E1, that starts off a matching, you sample E2. Can you add it to your current matching? If you can, add it. Sample E3, if you can add it, et cetera, et cetera. Okay? So if you assume you're processing this sequence of Snape samples, you can analyze that what's the probability when you get to the next sample, EI, that you add it to your current matching, that you get to augment your matching. If your current matching is smaller than you want it to be, if it's small o of K over T, then you can show that the probability you get to add this new edge is T squared over K. And so if you take K over T squared Snape samples, you end up with sorry, that should be K squared over T cubed Snape samples, then you end up with a matching of the right size. Okay, so that was matching. I hope I've convinced you that that was a really simple kind of sampling procedure, and the analysis to solve these kind of two hitherto unsolved problems really is not that complicated, even if you want to kind of flesh out the full details. But any questions? You can extend these to kind of weighted graphs. Everything works fine. Okay. How am I doing for time?
Let's say 7 minutes.
7 minutes, OK. Well, the other type of sampling, which I can probably fit into 7 minutes quite easily, called deals sampling. OK, so let me mention the results for this last part of the talk. So your dynamic data stream model, edges coming in, going out. You want to test whether your graph, if you want to test whether your graph is K edge connected, if between any pair of nodes there are K paths that don't share, if you want to test whether every cut in your graph has at least K edges, then you can do that using O tilde Kn space. And the basic idea is this deals sampling primitive. Now, in this PODS paper, so this is actually an older result. In this PODS paper, we extended this to node connectivity. So is it the case that between any pair of nodes, there are kind of K node disjoint paths? So our result here is that you can distinguish between graphs where the node connectivity is less or equal to K from graphs where the node connectivity is greater or equal to 1 plus epsilon K. And the amount of space that this requires is 1 epsilon Kn space. The basic idea is you combine kind of node subsampling, what we did in Snape sampling, with this deals sampling. It's an open question whether this business about distinguishing with the fact that 1 plus epsilon is really necessary. Like with edge connectivity, you can distinguish between K edge connectivity and K plus 1 edge connectivity in Kn space. I don't know whether you can do that for node connectivity. And lastly, we can construct combinatorial sparsifiers in a kind of a simpler way than that was done before that actually extends to kind of hypergraph sparsifiers. So what this means is that you see your graph inserts and deletes edges, and at the end of the day, you can 1 plus epsilon approximate every cut in that graph using space that's kind of roughly 1 epsilon squared n space. OK, so deal sampling. So deal stands for direct edges and add L0 sketches. So the simple problem I'll talk about first is, suppose you're given the task as the following task. You get to observe the stream of edge insertions and deletions, and then at the end of the stream, someone presents you with a specific cut, a kind of a partition of the nodes. And they ask, give me a random edge across that partition. Okay. This would be a simple problem to do if I told you the partition ahead of time. But if I tell you the partition at the end of the stream, how many people know how to do that? I'm glad you do. Okay, and my students do. Okay, so it seems like I can keep on giving. Okay, so this slide I've given way too many times. I'm very self-conscious about giving it yet again. But while people keep professing not to know it, I don't feel too bad. Okay, so I'll tell you the solution. Again, I'll tell you the solution in enough details that you can work out the missing parts without much hassle. So the algorithm again uses L0 sampling. So remember, L0 sampling is all about kind of a sketch matrix. So as the stream goes by, you're going to construct n projections, m times a1, m times the vector a2, m times the vector a3, up to the m times the vector an, where, as I said, m is a random matrix for L0 sampling, and ai is a vector that encodes the neighborhood of node I. And rather than formally define, let me show you an example. So if this is your massive graph, A1 is encoding the neighborhood of node 1. The way it does this is the vector has n choose 2 entries, so it's indexed by all node pairs. And the non-zero entries of this vector correspond to edges. So in the neighborhood of 1 is there's an edge between 1 and 2, and an edge between 1 and 3. And look, the non-zero entries of A1 is 1 and 2, and 1 and 3. Similarly, for A2, the non-zero entries in A2 should be 1, 2, and 1, 3. That's what they are, 1, 2, and 2, 3, and 2, 3. The only wrinkle is that for each edge, I arbitrarily pick one to be a plus 1 and one to be a minus 1. Okay? And I do this because then it has a nice property that if I'm interested in this cut, say, with kind of 1, 2 on one side and all the other nodes on the other side, well, look what happens when I add up the corresponding vectors, A1 and A2. I get this vector, where because of cancellations, I'm left with a non-zero entry in the 1, 3 column and the 2, 3 column. So 1, 3 and 2, 3. So by adding up the vectors, I can find the incident edges, or the edges across this cut. And this is more general, like kind of, if I sum up the vectors according to some arbitrary subset of nodes, that gives me the edges across the cut S to the rest of the graph. And because all the sketches I was doing was linear, if I then add up, so I've computed MA1, MA2, MA3, etc. So if I add up all the ones that correspond to i's in the set S, because M was linear, this is just the M times the sum. I've just shown that the sum, the non-zero entries correspond to edges across the cut. And because M is an L0 sampling sketch, it returns you a random non-zero entry. So by post-processing this, you find a random edge across this cut. If you use this primitive smartly, you can find, for your graph, you can find a spanning tree, so you can test whether the graph is connected. You don't want to arbitrarily test all cuts because there's exponential number of cuts, and that would be a nightmare. But you can do it smartly. You can also kind of extend this to, say, finding all edges that have small edge connectivity, or finding all edges, and a slightly more advanced result is finding all edges that have strong connectivity, according to using the definition of strong connectivity that Karga used. Okay, so as I said, this is actually an older result, but I wanted to mention two quick applications of this before.
The DL sampling is L0 sample per node, per vertex.
Yes.
That's what we call deals.
Yeah. So yeah.
Semantic, I wanted to know what they are.
I don't think it's a name other people should use.
And what was Draco?
It was actually for a different algorithm before I simplified one of the algorithms last night. Okay, so let me mention the applications of node connectivity. Rather than give you the node connectivity result I mentioned in the last slide, let's go for a simpler result. So the idea is that you read through the stream, and at the end of the stream, I'm going to ask you a query. And the query I'm going to ask is, are the nodes U and V connected in the graph if I remove all nodes in a set S? Okay? Which is kind of equivalent to, is there a path in the graph between U and V that avoids a set of nodes I'm now specifying to S? Okay? So let me show you how to do that using Densest sampling. So the algorithm, so you remember the algorithm for densest sub graph, sample some nodes and just analyzing that sample graph. And then the algorithm for matching, which was, densest sub graph, sample some edges, look at the density in that graph. The algorithm for matching was sample some edges and look for the maximum matching amongst the sampled edges. I'm not surprised you to learn that the algorithm for node connectivity is sample some edges and answer no, U and V are not connected after the removal of sets, after the removal of S, if there's no path between U and V that avoids S amongst the sampled edges. So again, the sampled edges are just forming, just playing the role of a kind of kernelization of the original problem. Of course, the devil's in what does sample mean. With densest subgraph, it was uniform sampling. With matching, it was Snape sampling. In this case, you pick each node of the graph with probability 1 over k, and then you construct a spanning forest on the remaining induced subgraph. And then you repeat this order k squared times. Again, a fairly kind of simple to describe sampling process, should be implementable in a variety of kind of models. The analysis is not too complicated. You basically just say, well, consider the path. Consider it as an example where the original graph did indeed have a path between U and V that avoided the set S. Okay? So what we want to argue is that there's still a path between U and V that avoids S in the subsample graph. Well, to do that, consider any two nodes along this path, say xi and xi plus 1, and observe that there's going to be a path between xi and xi plus 1 in one of these spanning forests if in one of the repeats of this algorithm, you sampled both endpoints, xi and xi plus 1, and you didn't sample any nodes in S. Okay? Because the guarantee was you're going to be returned a spanning forest. So if these two nodes were sampled, then this edge does exist. So sure, that's a path, but there's no guarantee that your sampling process would have picked up this simple path, but it's going to pick up some path between xi and xi plus 1. And that path is going to avoid all the nodes in S because all the nodes in S weren't sampled, so it can't have used any of those nodes. Okay, as I say, a little quick. Maybe you got it, maybe everything's fine, maybe you're caffeinated. If not, it's really something, it's easy enough to work out on the train back to wherever you want to go. Okay, last thing I wanted to mention was cut specification. So we can 1 plus epsilon approximate all cuts using that space. So at the level I'm going to describe this, it's not going to be clear quite what the difference is between what was being done before, but I'm happy to talk about this offline. So there's a nice result by Fung et al. From Stock 2011 that says if you sample every edge in the graph, like with probability kind of polylog divided by the edge connectivity of that edge, and look at the sampled graph, then all the cuts, and the sizes of all the cuts are preserved with high probability. And so one way you can kind of implement this idea in the data stream model is as follows. So you can use deal samples. So I said there's two immediate applications of deals sampling. One of which was to construct a spanning forest, and the other one was to kind of find all edges with low edge connectivity, So with small gamma, with small epsilon e. So basically, you can find all edges with lambda e being less than this, and definitely pick those. And for the remaining edges, sample them with probability of half. So some edges you sample with probability 1, some edges you're sampling with probability of half. No matter which case you're in, you're sampling with greater than this probability. So after this step, appealing to the Fungitel result, you've preserved all cuts. Okay. Now the graph is like kind of not sparse, but it's at least halved the density of the graph. And so if you just kind of repeat this log n times in parallel, we have a sparse graph. I think that's all I wanted to say. So thanks.